Hi, do you hear me?
Yeah, yes. Let's continue, please.
Uh,
Finished? Okay, okay. So,
so,
thank you for your welcome speech. Mhm. So, let's start. Um, okay, Alex, let's start. And let's go to our program. We have some small changes. So, is Alina Hnechuk is ready for presentation?
Good morning, everybody. Yes, I am.
Mhm.
Start sharing my screen.
Yeah, you may. Mhm.
Um, Can
We
everybody
can
see my
see
screen?
you. We can see.
Okay.
So you have up to 10 minutes, please.
Okay. Great. Thank you. Dear colleagues, let me present our research, intelligent information technology for decision support in player selection based on hybrid models. So let's start with formulation of the problem. The development of the contemporary elite sports industry is inherently coupled with the integration of intelligent information system and technologies. The processes of selection, evaluation, and squad assembly in team sports are complex multi-criteria tasks, which have conventionally relied heavily on coaching intuition and subjective expert evaluations. Nevertheless, the substantial uncertainty, dynamic sport environment, and requirements for simultaneous processing of massive datasets demand the development of objective, transparent, and reproducible tools. So the implementation of information technologies in preliminary selection processes allows for standardizing evaluation criteria, mitigating subjectivity, preserving the unique expert knowledge of the coaching staff, and partially eliminating the human factor from the routine stages of primary data processing. The development of comprehensive IT solutions for sport disciplines with a distinct role-based specialization becomes particularly relevant. A universal assessment of the entire team without considering player positions and tactical context lacks practical significance. Thus, the development of an effective information technology for coaching staff, small decision support in player selection must have been based on the systemic principles and approaches that have already been successfully validated in other critical domains. So the review of literature was done, and the contemporary data intelligent methods in sports are closely tied to designing systems that can handle data flows for both long-term planning and real-time match execution. The conducted analysis of scientific publications allows for stating that despite the large number of existing solutions, the general architectural and methodological problem of effective candidate selection remains unresolved. Limitation of existing method. So the first limitation is the black box problem in AI. Most deep learning models generate outputs without explanations, preventing coaches from understanding the algorithm logic and reducing trust in the system. Also, linear compensation effect. Critically low scores in key parameters, for example, poor discipline or incomplete injury recovery, are artificially offset by high technical skills, leading to erroneous selection decisions. Non-linear interaction. Conventional expert systems and simple weighted aggregation methods fail to capture the complex nonlinear relationships between a player's psychological state, tactical actions, and overall performance. Data scarcity, small sample size. Real-world club scouting is typically limited only to 3 to 5 candidates per playing position, making standalone machine learning mathematically unfeasible. Disregard for micro-context. Existing scouting platforms generate generic average player ratings that ignore position-specific requirements and individual club needs. Approach implementation. The implementation of the proposed approach relies on the two-stage structure of the information technology. The first stage involves employing neural network models to identify the latent parameters, predictive potential of players by analyzing primary sport statistics. In the second stage, the generated evaluation vectors are fed into the multi-criteria decision-making loop for the final ranking of candidates according to specific tactical requirements. With two-component framework addresses the law of interpretability black box problem of neural networks, providing the coaching staff with well-bounded and fully transparent analytical toolkit. The proposed intelligent decision support information technology features a modular structure. It provides end-to-end processing of athlete data ranging from the automated collection of primary parameters to the calculation of the final candidate ranking. The system architecture is structured into four functional layers, each based on a specific mathematical apparatus and artificial intelligence methods. Conceptual architecture on intelligent information technology for decision support in player selection based on hybrid models are now shown on the slide 7. The system operation is initiated when raw data is read from primary sources, such as protocols and video materials. The input parsing and normalization model performs synthetic analysis, cleaning and scaling the data, after which the single data stream branches into two parallel pathways for processing features on different natures. The left branch of the system is responsible for processing the first group of parameters, which include the athlete's basic indicators such as anthropometry, physical fitness level, general characteristics, and competitive performance result. This data directed to the first level production counter. Here, utilizing an expert knowledge base and if-then logical rules, the system performs simple filtering, namely the binary screening of candidates based on their compliance or non-compliance with the established criteria. Concurrently, the right branch processes the second group of parameters, which encompass more dynamic and complex metrics, technical and tactical actions, special training level, and psychological indicators. These data are passed to the second level neural network contour, where an artificial neural network performs a search and identification of hidden nonlinear dependencies within the structure of technical and tactical actions. And the output of this contour, the athlete's predicted potential value Y, is generated. Subsequently, the analytical streams for both contours are integrated within the results integration and synthetic model. This block performs data aggregation, converting the deterministic counter value P and the probabilistic neural network output Y into a single normalized ranking scale using a mathematical formula. The generated final candidate ranking is transmitted to the highest level of the architecture, the presentation layer. The end user interacts with these results through a user interface in the form of interactive dashboard, which provides both a clear visualization of the final ranking and a detailed analysis of the selection rationale for each candidate. To evaluate the practical effectiveness of the developed hybrid intelligent decision support technology, an experimental verification was conducted using a representative sample of 30 young volleyball players. Primary data streams were extracted from competitive match protocols and digitalized video materials. The input parsing and normalization model successfully executed synthetic data analysis, error cleaning, and min-max scaling to transition indicators in a unified numeric range. The processed data streams was partitioned into two parallel feature sets to befit distinguished processing contours of the architecture concurrently. The obtained results confirmed the capability of the developed intelligent information technology for decision support in player selection based on hybrid models to resolve the structural limitation inherent in existing system. Now, the first one is the black box problem. The developer took contour architectures into its level 1 structure, with which function based on transparent logical if-then rules enable the integration of strategic expert coaching knowledge with automated computation, ensuring a clean and human understandable decision-making. The linear compensation effect of critical deficiencies. The developed technology addresses the artificially offset problem by utilizing the level 1 production rules such as strict binary filter, fits or not fit. If a candidate fails to meet the baseline function or behavior requirements, the ranking counter P drops immediately, or the candidate is executed from the preliminary stage. Identification of lantern nonlinear relationship. To capture this dimension, the right analytical branch introduces an artificial neural network module specifically tasked with processing the second group of dynamic parameters. This network successfully identifies hidden nonlinear performance patterns that cannot be formalized during manual rule setting. The data scarcity and small sample size handling In practical club operation, the scouting and selection activities are restricted to small sample size, only 3 to 5 real candidates. The proposed hybrid framework bypasses the feasibility of such limited dataset by modifying the neural network objective. Instead of calculating relative pool statistics, it performs multidimensional projection of the individual athlete's potential value Y. This predicted value is subsequently consolidated with the deterministic rule-based counter P within the results synthetic loop to generate accurate rankings regardless of the sample of scarcity. The context, awareness, and positional specificity, the developed information technology is entirely customized around role-based athletic profiles. Furthermore, the system remains fully content-dependent, allowing coaches to dynamically alter rule constraints and criteria weight depending on current goals, such as preparing for specific short-term tournament, etc. Based on the experimental processing of the athletes dataset, the hybrid system successfully classified the candidate pool into 3 distinct structural groups: players with high technique but low discipline, physically gifted players with weak technique, balanced players. So to interact with this analysis results, an interface in the form of interactive dashboard is proposed. Example of the visualization of such profile for candidate 7 who achieved a second place in the experiment group is shown on the slide number 10. Furthermore, to demonstrate the system capacity to eliminate linear compensation errors on practical level, this details a comparative evaluation case involving candidate number 12 who presented exceptional technical mastery paired with a critical behavioral efficiency. The table of comparative analysis evaluating of a candidate with critical deficiency you can see on the slide number 11. So the conclusion you can see on the slide number 12, and that's all. Thank you for all of your attention.
Thank you, Alina. And dear colleagues, do you have a question to presenter?
May I have one?
Of course.
Yeah, sure.
Alina, tell us please, how were the if-then expert rules for the first level of the architecture collected and formalized, and to what extent they are subjective?
Thank you for your question. So the knowledge base was developed through collaboration with experienced volleyball coaches and domain experts. Their practical experience was formalized into explicit if-then production rules representing the club's recruitment philosophy. Also, some degree of subjectivity is inevitably present during some of the rule formulation. This is actually one of the strengths because for the hybrid approach, as it preserves the specific coaching philosophy and it helps to create organizational strategy for a particular volleyball club. This subjectivity is balanced at the second level, where objective statistical match data are analyzed by artificial neural network. So the synthetic model integrates expert knowledge with data-driven prediction, producing balanced and well-justified recommendation.
Thank you so much for your answer.
Thank you.
Okay, colleagues, no more questions? Okay, so let's move on. Okay. According to program, the next presenter is actually me. And let me share my screen. Do you see my presentation?
Yes.
Okay, thank you. So, actually, in the current condition of full-scale war in Ukraine, the number of people who have been injured and have impaired motor function is rapidly increased. This creates an urgent need for effective, accessible, and scientifically based rehabilitation. So, in this case, traditional method for physical rehabilitation, although they remain the basis treatment and they have some drawbacks. That's why integration of the latest digital technologies into a process become not only relevant but also critical necessary. Virtual reality has a significant potential as a rehabilitation tool as it allows the creation of safe, controlled, and repeatable environment for training motor function. So, therefore, creation for an inclusive VR simulator with adaptive complexity is a relevant scientific and practical task that meets modern intelligence into the field of medical rehabilitation and can significantly improve the quality of life of thousands of people affected by the war. In this case, we proposed to make some methods that aim to increase the efficiency of inclusive trainers for motor function recovery. In this case, of course, made state of the art had 3 directions on the and 1 gap. First, it's intelligent adaptation, take into account machine learning based technologies, attachment tune task parameters from kinematic and psychological data. Another direction, it's fuzzy logic and multimodal detection, which enables to adjust load in real life. Also, system with meta analysis that confirm immersive VR performance. And the main gap that all these approaches have no clinical validation separately, and no unified method combines high-frequency telemetry, qualified functional status, and real-time adaptive difficulty in one inclusive virtual reality trainer. From this point of view, our team proposed a new method which take into account 6 parameters of telemetry: position, orientation, velocity, acceleration, control state. After then, we have to take into account the set of features: moving, motion phase, segmentation, tremor spectral analysis, reaction time. Take into account functional status, evaluate weighted score of range of motion, strength, coordination, and stability. And after having these data, we have a possibility to evaluate adaptive difficulty. It's a real-time adjustment of target distance, size, height, and speed. Making this loop, we can update difficulty and functional status trying to feed the next training block. So let's go to 6 proposed steps. The first one is initial diagnostics and calibrations. At this stage, system runs calibration exercises to establish reference amplitude, speed, coordination, and tremor. We take into account healthy limb reference come from its own performance, and for bilateral injury, normative age, sex, conditional data are used instead. The next step includes continuous telemetry capture. During this step, the system records fixed controller position and orientation in real time, and every moment we have full state vector is logged: position, orientation, linear and angular velocity, and trigger grip button state. After that, we have a possibility to make adaptive difficulty correction. You can obtain functional status score and its trend. The system automatically adjusts task difficulty. Difficulty is expressed through 4 game environment parameters such as target distance, target size, target height, and for some dynamic text, target movement speed. After that, we are to generate detailed progress report and make some differences for a graphical visualization of every functional status component over time, comparison against previous sessions, and the recommendations for the next training regimen. So here I present some math for qualifying function and adapting difficulty. So we are eager to evaluate weighted blend of normalized range of motion, strength coordination, and stability, as well as evaluate success metric. It combines hit accuracy, completion time, and movement smoothness, as well as weight shift from accuracy towards speed as therapy progress. If average success exceeds some target threshold, we have ability to raise difficulty, and if the patient struggles, it falls. Also, we can evaluate step size guard. We can cap any single change up from 10 to 15%, preventing difficulty spikes that could cause during the re-injury or fatigue. As an implementation, the VR system of MetaQuest 3 was used, and using Unity, some programs was for this VR system was evaluated. So having this, we obtained some experimental result. The main feature was to obtain throw speed profile, trigger activation, movement map, vertical motion profile. In this case, participants roll virtual darts as static targets placed from 2 or 3 meters away from the and from meter to 1.8 meter high. It's a range engaging the shoulder, elbow, and wrist. Telemetry from the high right controller was logged as 70 Hz. So as a result, we obtained 47% of vertical amplitude difficult found, and time to peak through speed with the normal from 1 to 1.5 seconds range. As asymmetry threshold between limbs flagged as clinically significant is up to 20%. So as a result, we obtained up to 25% of detection accuracy on functional limitations, and 82% of adaptability score. Talking about telemetry completeness with 15 different tracked motion parameters, we obtained up to 84%. It's integral efficiency. So we tried to improve method unifying different motion telemetry parameters, as well as quantified functional status and real-time adaptive difficulty in one inclusive virtual reality trainer. We used MetaQuest 3 VR a device logging 15 different biological parameters and had some not bad results. Of course, there are huge limitations because using this virtual reality device and system, of course, it must be evaluated during the presence of specialists, because all protocols are provided by medical environment must be obligatory. So thank you for your attention. Maybe you have some questions.
May I ask question?
Please. Yeah, please.
It's very interesting. I have a question about personalization. How different patients are differentiated in your system?
Actually, the system actually does not personalize patient. The main role in this system is to help to medical personnel to make some protocol movements, and of course, the medical professional environment is adjustment make adjustment for different person. So it's not automatically. It's chosen by some medical staff to make different movements, different, and the main idea to find out the progress of maybe some improvements or decrease in some treatment. Thank you for your question.
Thank you.
Okay, so let's move on. So the next speaker is from the team with speech adaptive graph-based context-aware decision model for intelligent information systems. Who will be presenter?
Hello, I will be the presenter.
Hello, Maria, please.
Yeah, let me share my screen. Do you see my screen?
Yes, we see, but please launch slideshow.
Yes.
Okay. Yeah, sure. You
Hello.
have 10 minutes, please.
Okay, hello. I would like to present our research entitled Adaptive Graph-Based Context-Aware Decision Model for Intelligent Information System. This work primarily focuses on improvement intelligent decision support system operating in enterprise environments where contextual conditions continuously evolve over time. Traditional decision-making approaches usually rely on either predefined business rules or on standalone machine learning models. Although both approaches are widely adopted, neither is sufficient robust when user behavior or data distributions change dynamically. In this work, we propose an adaptive hybrid decision model that combines symbolic reasoning, supervised machine learning, and graph-based similarity retrieval using hierarchical navigable small world graphs, or HNSW. During this presentation, I will briefly introduce the motivation, describe the proposed architecture, and present the experimental evaluation to summarize the obtained results. Here you can see the motivation. Intelligent information systems are becoming increasingly important in enterprise applications such as customer relationship management, recommendation system, and business analytics. This system continuously receive information from multiple heterogeneous sources. User interactions change over time. Customer preferences evolve. That means that business environments are become increasingly dynamic. Conventional rule-based systems remain attractive because they are transparent and easy to interpret. In other words, business experts can clearly understand why a particular decision was made. However, such system cannot automatically adapt when contextual conditions change. Machine learning models address this limitation by learning from historical data. Nevertheless, their predictive quality often decreases when the statistical properties of incoming data differ from the training distribution. This phenomenon is commonly referred to as concept drift, or in other words, distribution shift. Consequently, non-purely symbolic reasoning or purely statistic learning are not sufficient for dynamic environments, and that's why our motivation was to design an adaptive decision model capable of exploiting contextual information, predictive learning, and similarity reasoning simultaneously. Here you can see the research gap, and after analyzing the recent literature, we identified an important research gap. The research gap is that machine learning models often rely on symbolic reasoning, while intelligent information systems rely on that numerous hybrid decision models combine business rules with machine learning algorithms. These approaches improve predictive quality compared with purely based system. However, very few studies integrate graph-based approximate nearest neighbor retrieval directly into the decision-making process. Similarity search has become extremely popular in vector databases, also recommendation systems, and semantic retrieval. Modern graph structures such as HNSW provide very efficient retrieval, even for millions of high-dimensional vectors, but nevertheless, these methods usually operate as independent retrieval engines rather than as integral components of adaptive decision support architectures. As a result, existing intelligence systems often remain vulnerable when contextual conditions evolve. Here you can see the proposed adaptive decision model, and our entire framework consists of 4 sequential processing layers. Everything begins with contextual information collected from enterprise information systems. This information may include customer behavior, interaction history, demographic attributes, temporal information, etc. This layered architecture combines interpretability, statistical prediction, and contextual similarity reasoning within the coherent framework. On this slide, you can see the overall architecture of the proposed model. And let's go through this scheme. During the first stage, heterogeneous contextual attributes are transformed into a unified high-dimensional numerical representation called the context embedding. Next, a rule-based layer applies predefined business constraints. This layer removes ineligible entities before computationally expensive processing begins. The filtered instances are then analyzed by a supervised machine learning model. In our implementation, we employ a random forest classifier that estimates the probability of a positive response. Simultaneously, the context abandon is submitted to a graph-based similarity inference layer. Here, the HNSW graph efficiently retrieves historical similar cases and estimates their average response. Finally, both probabilistic estimates are combined by the adaptive fusion layer, producing a single decision score that is later used for ranking or binary classification. Context representation and adaptive fusion. One of the key contributions of this fork is the representation of the context in a unified numerical form. Instead of processing each attributes independently, all contextual information is encoded into a single high-dimensional vector. This representation allows both the machine learning model and graph-based similarity storage to operate within the same feature space. The random forest classifier estimates the probability of a positive decision using global statistical relationships learned from historical data. In parallel, the graph retrieves the most similar historical entities and estimates the expected outcome according to the observed behavior. Unlike conventional hybrid systems, the contribution of each component is not fixed. Instead, the weighting coefficient depends on interaction freshness. Recent customer interactions generally contain more reliable behavioral information. Therefore, the supervised model receives a higher weight. Older interactions rely heavily on similarity reasoning obtained from neighboring historical examples. And this adaptive balancing mechanism enables the model to remain robust even when contextual conditions change. About the experimental evaluation. To evaluate the proposed architecture, we used a synthetic serial-like dataset containing 50,000 interaction records. Each record included both numerical and categorical contextual attributes that we described previously, and this dataset was intentionally designed to simulate the realistic enterprise environments while allowing to complete control over contextual evolution. And this evaluation consisted of 2 phases. During the first phase, all models were evaluated under stationary conditions. And second phase, we introduce a controlled distribution shift by modifying relationship between contextual variables and campaign responses. This approach allowed us to analyze how well different decision models preserve predictive quality when contextual conditions change, and we compared 5 approaches. The first approach was a purely rule-based system. The second deployed by only the random forest classifier. Also, we elevated a conventional hybrid rule plus random forest architecture together with 2 graph-based hybrid models based on FAISS and HNSW similarity retrieval. Performance was assessed using a standard classification matrix, including accuracy, precision, recall, F1 score, and AUC, while computational efficiency was measured through inference latency. This slide summarizes the most important experimental findings. Under stationary conditions, the proposed HNSV hybrid architecture achieves the highest predictive quality among all evaluated approaches. More importantly, we evaluated all models under controlled distribution shift. This experiment simulates real enterprise environments where customer behavior gradually change over time. In contrast, the proposed adaptive architecture successfully compensated for the contextual changes. The next slide evaluates predictive performance under stationary conditions. The purely rule-based model demonstrates limited classification capability because it relies only on predefined business logic. And the next slide compared with FAISS, the proposed implementation also requires less memory while providing higher predictive quality. And conclusions: to conclude, this research introduced a novel adaptive graph-based context-aware decision model for intelligent decision support system. The proposed architecture integrates 3 complementary paradigms. First of all, symbolic reasoning ensures interpretability and compliance with business rules. Second, supervised machine learning captures global statistical dependencies from historical observations. Third is that graph-based similarity retrieval introduces a contextual reasoning. And furthermore, the computational overhead introduced by a graph-based retrieval remains sufficiently low to satisfy practical real-time requirements. As a future work, we plan to evaluate the proposed model using real enterprise datasets, investigate online learning strategies, and integrate reinforcement learning for adaptive fusion, or explore dynamic optimization of graph indices. Thank you very much for your attention.
Thank you, Marianne. And dear colleagues, do you have any questions to speaker?
I have a question.
Please.
Thank you for interesting presentation. How many rules are there in your system and who created them?
They are created manually. For example, we used a business rule to exclude the lead from campaign when not the prediction when the numerical parameter was not enough to include the customer in prediction. For example, the number of goods the customer is likely to buy.
How many rules?
For our investigation, we used maybe around 5 rules, but it can be easily extended.
Thank you.
Thank you, Marianne. Colleagues, no more questions? Okay, let's move on. So the next presenter is somebody from the team, a geometry-aware data anonymization method for medical text embedding in distributed rack systems. Who will be speaker?
Me, Pavlo Zamroz. Thank you.
Yes, Pavlo, please.
Yeah, let me share the screen. Oh, I cannot. Somebody's sharing the screen because I cannot share the screen. Hello, can you hear me?
We see your screen, but we do not see your presentation yet.
It's not my screen. I cannot share the screen. I cannot share the screen, so I don't know why. Sorry, can you skip me for this presentation? I mean, I will be next one. I give the place to
sure.
whatever
Okay.
was.
Yeah,
I will try to reconnect. Sorry about that.
It's okay. Okay. Olena, Haitan, are you ready?
Yeah, I need 1 minute to share the screen.
Yeah, sure.
Do you see my screen?
Yeah.
Yes, sure. Please.
Okay.
You have 10 minutes, please.
Can I start?
Yeah, sure, please.
Okay. Hello, to your attention is offered report on the topic development of a model for assessing software reliability characteristics based on the use of fuzzy inference with neural network configuration. Ensuring software quality is one of the most crucial tasks for modern information systems. Software reliability is one of the pivotal indicators considered in the most existing software quality assessment methods and models. Modern reliability assessment models are mostly based on the use of complex approaches to take into account software defects. It is therefore proposed that existing approaches to the software defect prediction be improved by developing and applying intelligent systems based on fuzzy inference systems with the possibility of retraining. Such system can be used both at the stage of software development and at subsequent stages of the software life cycle, considering the individual characteristics of the software build or version. The general structure of such systems is shown in Figure 1, which includes the following stages of operation: data collection, fuzzification, fuzzy inference, defuzzification, and output. For example, at the software development stage, work within development team can be organized using the Git version control system. A general overview of the intermediate stages of development using Git flow is presented in Figure. The use of data on detected defects and prediction data for each release will allow for the selection of the optimal option for further software development or its correction. The monitoring process is conditionally divided into a sequence of discrete time periods I from 1 to k of equal duration. During each period, any detected defects are recorded and the total number of defects k is calculated. It is believed that such monitoring for defect detection is carried out on the ongoing basis. This approach will allow the necessary data to be collected for further model operation. Subsequently, the structure of ICyberPhyS with input parameters, each containing two triangular membership functions, will have the form presented on the slide. Okay. The ICyberPhyS structure is shown in figure, and it includes 5 layers. Each layer is used for fuzzy logic inference to predict the number of defects in the software instance during the I prediction part of the prediction time interval. The data for ICyberPhyS training can be collected by monitoring the defects that have been detected at each stage of the software life cycle and forming such a structure. Training of the ICyberPhyS model is based on the data for discrete observation intervals and can be performed in MATLAB. The results of the training is the determination of the values of the corresponding parameters of the membership functions for all input values and the coefficients for the subsequent identification of the individual fuzzy outputs of the fuzzy production rules P. As you see, we have 16 production rules. So, the paper proposes an approach to creating a model for predicting the number of defects in a software instance based on the application of artificial intelligent models, specifically fuzzy systems with a neural network configuration. The ANFI structure for predicting the number of defects in software instance during the entire software life cycle or part of it is proposed. The requirements for the set of data necessary for the correct training of such a system are identified. This makes it possible to resolve the issue of developing mathematical support for the synthesis or improvement of software defect prediction models. The scientific novelty of the obtained results lies in the improvement of the structure of the narrow fuzzy prediction model, which, in contrast to existing models, takes as input parameters the number of defects for previous periods and the average moving number of defects from the beginning of monitoring. This allows for the prediction of the numbers of defects to be made with the consideration of the individual characteristics of a particular software instance. Furthermore, the proposed model can be easily scaled to achieve the required accuracy. The practical significance of the obtained results is that using the improved model based on FIS allows for calculation of the value of the software reliability indicator, thereby ensuring early decision-making on further directions of its development or updating. Ultimately, this allows for provision of better values of the quality indicator of the software instance. Thank you very much for your attention. I'm ready for your
Thank you,
questions.
Lana. Thank you, Lana, for your interesting presentation. Dear colleagues, do you have any questions? No, I have one. Alana, please say, what are the main limitations of your research?
Our model was trained only on known data set, and I think that we need an additional research to look for the acceptance to other data sets. Now we integrate an automatical configuration of parameters, and their weights are tuned automatically. But we need an additional research to be sure that this tuning will be suitable for each data sets.
Thank you. Okay, thank you. Let's move on. Okay, Pavlo, are you ready?
Yeah, let me try one more time. Yes. Now you can see my screen, or can you see my screen?
Yeah, sure, please. Up to 10 minutes, please.
Yeah, thank you. Thank you, everyone, and good morning. So my name is Pavlo Zamros. I'm from Lviv Polytechnic National University, and I'm going to present the geometry of our data analyzation for medical text embedding in distributed RAG systems. What does basically mean? It's how to say it. Nowadays, a RAG system can store potential records, patient records as embedding vectors in the cloud, and we show how to protect those vectors from the reconstruction attack without breaking the search, and that makes them still useful. So let me start with the problem. So during our research, we faced one issue, I would say. So modern clinical record system encode each patient record as a high dimension embedding vector and store those vector in a cloud vector database. This lets language model retrieve the patient specific information in real time without retraining and so on. But the problem here that those vectors are not safe by default. As we know, not everyone, but most of the in this field, there are vector text and zero to text. It's models or tools that can reconstruct the original text, including the protected health information. Here is the key inside of our work. It's the risk is not uniform because records of the common condition sit in dense region of the space surrounded by many similar records. But the records of the rare diseases sits in space geometry, sorry, isolated region. And that isolates makes them far easier to detect, far easier to retrieve, and so on. So that's the issue, that attackers can still get your information, especially if this information is unique. I mean the health information. In this slide, you can see that NAR reduction, it means when we remove all PII or PKI information from the original text, diseases, diagnoses, and so on, we still get 71 and 4% leaks, even if we remove absolutely those personal identification information. But if we do global differential privacy, add uniform noise to destroy, how to say, this success retrieval rate, we still get we have drop in the search to 64 and 9%. It's only the rate that can return us a correct information. As attackers can do or cannot. Sorry, let me be precise about the adversarial we defend against. We assume that attackers has a full read access to the cloud vector database, and maybe they can get this access. Maybe this can be some public database or whatever. They can see all the anonymized vectors and black box query access to the embeddings models, so they can submit any text, any observe the vector it produce. So what attackers does not have is equally important. No model weighs gradient or training the data, no access to the on-premise side of our gateway. So they cannot reach the things. And also they don't have access to the original clinical text that some clinics store, the raw text before anonymized vectors. This is a standard vector text in the model, and it's strictly stronger than the text requires it. Our defense makes no assumption about which attack is used. We evaluate from both of attacks by anonymizing the data and also making those vectors more rare, so attackers cannot the weight of the vectors become not so how to say precise. So here the pipeline let's move on. Here one of the method is the protection is protection to the risk. We used a lead. Lead is a local in strict dimensionality. It's to find geometrically isolated vectors. I mean, geometrically, this isolated vectors is raw data of some particular patient, or it depends on the clinic's data. It can be a huge amount of information, but some unique diseases, it can be some particular disease and particular vectors. So what we proposing to do here is to shift these unique vectors more to the group of the vectors that to protect it somehow, but still be useful to for search for or some LLMs or another tools that can use RAGs, and they still can get valid information. So in here, here it's a pipeline. They have 4 stages. Stage 2 and 4, that's in amber color, are core contributors here. Stage 1, it's a graph construction. So we build car nearest neighborhood graphs over 35,000 references embeddings. It's public available, how to say, records that we can train our model or use it in some things. So it's not real patient data here. What does it mean? After the building the RAG database, it's done once offline. Then stage 2, it's vulnerable assessment for each incoming record. A named entity module flags to the health information, and the lead scoring decided whether the embedding is genomically isolated. That is our risk signal. So we store in stage 3, tangent space estimates with the Lego algorithms. We estimated the local geometry of the manifold from gradient of the Laplacian Lego and SVD. This tells us in which direction along the data we can safely move this vector closest to the group of the vectors. In stage 4, the geodesic shift. We relocate this vector along the manifold with a magnitude scaled directly by its risk score. Let's move on. So here it's adaptive protection. And you can see here how this in this image you can see how we're detecting vectors moving before and what's happening after. So some unique vectors moving closer to the group. I won't stop here much more. Here it's our experiment setup. What we did, we used the Mimic 4 clinical nodes. So there are more than 35,000 nodes for test, as I told before. We used vector-text embedding and zero-to-text embeddings. It's a how to say, tools that give us possibility to try to extract the data from the RAG system. Also, we use the metric, it's inversion success rate, and our protocol, it's 5 random seeds, latency over 1000 after vectorization. And our results here, that's what we got. Across all records, the inversion success rate, ESR, drops to 2% under vector-text attack from draft 87 that we saw before. I mean, it's huge drop, but only between the how to say not protected data at all. At the same time, recall at 10 says at 92%. So it means that this data still useful, so we can get some useful information from this RAG system. So, and the most important number is the third one for rare diseases record. It's only less than 1% that can be retrieved. And the latency, as you can see, it's also not so big one. Here you can see the comparison of all this metric that I mentioned before, but more, but a bit more precisely. So you can see here vec to text, zero to text, unprotected baseline. It means that it's just raw data stored into the RAG system, and those vec to text and zero to text, with those tools, we trying to extract some information, and it was successful in 87.1% and 91.5%. So when we used only reduction, we still have a bit success rate based on the context of the medical records. We can still extract a lot of patient information. When we do the global noise extraction, much more smaller, but our information becoming less useful, only 64.9% from the data that we used. Sorry, and what we proposed is showing us actually pretty good numbers. As you can see here, ESR only 2%, or let's say it's near 4% in better model zero to text, but we still in 92% can have useful information. Of course, it's a bit longer than other methods to extract some information, but maybe it's worth it. So, and moving to the conclusion, what we done here, and actually what's more important is the new steps. What we done here, I actually describe it. So we prepared geometry-aware vulnerable adaptive anonymization for clinical RAG embedding. As you can see in our experiments, it reduces inversion pretty much, protect the records, and dropped in gateway model, so we can give this data to somebody else to analyze and so on, but we can be sure that those data are protected. But for future work, it's what we're trying to do. It's use this framework with some clinic as a pilot, formal differential privacy style, because it should be formalized to guarantee that this geodesic shift works and everything else. But what most important, we have to perform much more experiments using not only English records, but in Ukrainian and other languages, and maybe try to use some real data, but it's pretty tough in medical field. But that's it for my presentation. Thank you all. And ready to your questions.
Pavlo. Thank you, Pavlo, for your presentation. Dear colleagues, do you have any questions?
I have a question.
Yes, please.
How do you estimate the computational resource costs of the proposed method?
Computational resources, I mean the price, how it should be, or we're talking about the latency?
Latency is one aspect, and memory consumption and other resources.
Actually, I didn't calculate it yet because I used a lot of models and so on. I mean, to prepare this rack system and to fill up it with the data, probably it will use a lot of memory and computation costs, but I didn't calculate it yet. But what most important for this research, it was how end user can extract some useful information for him from this rack system using some prompt. So this was calculated, and it's near the half of the second.
Thank you.
Thank you for your question.
Okay,
And
thank you.
Я хотів би дати
So,
питання.
Yes, Vasil. Yes, please.
Професор Чигінь, Львів, політехніка. У вас Петро, так? Павло. Павле, у вас на вашому одному слайді є затримка 49,6 мілісекунди на процесорі, командлі ЦПУ. Скажіть, будь ласка, це чистий час обчислення моделі? Чи сюди вже врахована затримка передачі даних від сенсора до хмари? Дякую.
Це повністю час від і до. Тобто від моменту запиту до моменту відповіді отримання самих даних. Але це, знову ж таки, залежить від даних, наскільки вони збалансовані, наскільки їх багато. З тими даними, які використовував я, затримки в середньому були такі.
А які сенсори, які датчики саме ви використовували?
Я не використовував сенсорів і датчиків, тобто це система RAC, по суті, бази даних, яка знаходиться в клауді, де збережені рекорди, ну, тобто записи пацієнтів. І запит ішов з комп'ютера, тобто, умовно, давайте приклад, лікар хоче дізнатися більш детальну історію за свого пацієнта. Він дає якийсь промпт або, ну, неважливо, тобто якийсь запит, квері, оцей пошук. Від моменту цього запиту до моменту, коли він отримує якусь інформацію, було 49,6 мілісекунд. В середньому.
Тож реальне вимірювання ви не робили, так?
Ну, скажімо так, запитів було багато.
Температури.
Ні, це те, що я робив, ну, і те, що насправді важливо, яка буде швидкість відповіді до користувача.
Okay, thank you. So the next report is devoted to development of multimodal architecture for the intelligent software module for people with visual impairments. Who will be speaker? Olena, please.
One second.
We do see your presentation.
Okay. Okay. Excuse me. Okay. Dear colleagues, I present work development of multimodal architecture for an intelligent software model for people with visual impairments. The need for accessible, autonomous, and context-adaptive assistive technologies has become crucial due to rapid growth of the visually impaired population worldwide and particularly in Ukraine due to the war. According to the World Health Organization, more than 2 billion people worldwide have visual impairments, and approximately 300 million had moderate or severe impairments, and 43 million were completely blind in 2020. In Ukraine, according to official statistics, the number of blind people has increased from 20,000 to 70,000 people during the war. It's only official statistics, and the real situation is worse. These numbers are increasing during the wounds, explosions, and aging population, diabetes, and other factors. Assistive technologies play a key role in ensuring equal opportunities for people with disabilities. Development of AI and machine learning opens up new opportunities for creating more intelligent and adaptive accessive technologies. However, despite significant progress, modern solutions serious limitation. Its algorithm accuracy, energy consumption, consistent operation of camera, GPS model, sensors, and constant data exchange go to rapid battery drain. Its interface usability, social and cultural factors. An analysis of the technical implementation of existing model assistance reveal a number of problems related to the algorithm accuracy in uncontrolled conditions. And the purpose of the paper is to develop the architecture of an intelligent software model that supports users with visual impairments, ensuring effective multimodal interaction and reducing cognitive load when using digital technologies. Most software tools for visually impaired people are based on two dominant architectural approaches. It's linear navigation and cloud data processing. The first approach, implemented in screen readers, is based on intercepting systems events and converting them into synthesized speech. The second approach has gained popularity with development of AI and is represented by computer vision systems such as Seeing Eye, Google Lookout, Envision Eye, and others. And this system can analyze visual scenes and recognize text and objects. But as table shows, none of the existing products offer all necessary tools in a single interface. The main issue of existing solutions is that they overload their auditory perception channel. People with visual impairments rely on their hearing to navigate and monitor their safety. However, when app continuously generates voice messages, it creates a conflict of attention, which leads to cognitive exhaustion. Users are forced to choose between receiving information from the device and controlling their environment acoustically. Localization and integration with local infrastructure are separate issues. Most global products don't support Ukrainian language. The developed system, Providnik, is designed to fill this niche. It combines the functions of visual analysis, full navigation, hazard warnings, and complete Ukrainian localization in a single form factor, which can be implemented as a mobile application based on Raspberry Pi. The key task was to create an architecture that ensures accurate recognition of information and effectively distributes the user cognitive load while ensuring autonomous operation. The proposed model is based on the concept of multimodal augmentation, involving the simultaneous use of several communication channels: voice, tactile, and gestures. The architecture implements the principle of redundancy and complementarity of information, adapts the system to the current context, and reduces cognitive load. Critical safety messages are duplicated through vibration, enabling users to react without interrupting the reception of other information. The voice interface is used to convey semantically complex data, such as reading text, while gestures ensures interaction in public places. The architecture of developed software is based on a modular principle, which ensures flexibility on configuration and the ability to update components independently. The system consists of the four basic interconnected blocks: data collection subsystem, processing core, context engine, and multimodal output subsystem. The data collection subsystem is responsible for receiving input information from sensors, including the video stream from camera, audio signal from microphone, and data from sensors. The obtained raw data is transferred to the processing core, which contains neural network models for computer vision and natural language processing. A key element is context engine. This component analyzes factors such as type of recognized objects, noise levels, time of day, and user behavior patterns to prioritize information and determine how it should be presented. For example, when system recognizes text in document, it activates reading mode. Filtered information is sent to output subsystem, which generates synthesized speech, sound signals, or vibration. Simply listing all objects overwhelms user with information. To address this issue, Context Engine interprets the scene and determines the relevance of the information. In street mode, for example, priority is given to dynamic objects, it's cars or pedestrians, and potential obstacles, while architectural details are ignored. In indoor model, the focus shifts to identified doors, furniture, and household items. To solve the problem of internet dependence and ensure data privacy, architecture provides for performing computational operations directly on the user device. Using edge computing. Quantization and pruning methods reduce model size and RAM requirements. The voice user interface is the primary channel for transmitted semantically complex information. To minimize cognitive load, the system of short, intuitive commands was developed that allows users to quickly switch between modes without having to navigate complex menu. Special attention is given to ensuring the confidentiality and social acceptability of voice interaction. In public places, the constant vocalization may be undesirable. So, to address this issue, support for earcorns have been implemented. To reduce the load on the auditory channel and ensure discrete interaction, a haptic feedback module had been integrated into the system. It uses the vibration motor of a mobile device to transmit special information and warnings. The Zeshind interface serves as alternative to voice commands and buttons. We choose the CNN architecture optimized for limited computing resources to implement computer vision on mobile platforms. Object detection is performed using a modified tiny YOLO architecture. This model strikes an optimal balance between precision and frames per second, ensuring smooth feedback during navigation. In parallel with object detection, and optical character recognition functions have been implemented to read printed text. To improve recognition accuracy in challenging conditions, algorithms for preliminary segmentation of text blocks and image preprocessing are implemented. Here you see the screenshots of Providnik in Ukrainian localization. It's offline object identification and voice recognition in real time, and integration with Gemini and Google Maps when connected to the network. A critical step in developing the model was applying participatory design methodology, which involves the active participation of end users in all stages of development, from requirements to usability testing. The research included a series of interviews and tests involving people with various degrees of vision loss, including military personnel undergoing rehabilitation. To evaluate the effectiveness of intelligent software model, a three-stage experimental study was conducted. The first stage evaluated performance of the recognition models under real-world conditions. On the stage of practical testing of the developed application, the research team performed navigation tasks with blindfolds to simulate visual impairment. And on the last stage, the usability evaluation involving people with visual impairments from the local Society of the Blinds was conducted. The effective of the proposed approach was confirmed through the conducted experiments. The object detective module reaches 87% accuracy on thin text and 94% of text recognition accuracy. The use of temporal coherence and confidence filtering reduced false positives by approximately 9 to 12%. Adaptability to different situations and contexts of use is ensured by context-aware processing pipeline, its read and indo modes, which prioritizes relevant object classes and interaction modes. This approach reduces non-essential notification by about 30% and lowers auditory cognitive load. Practical usability is achieved through the energy consumption optimization and offline operation capability. Model quantization pruning reduced model size by 43% and decreased battery consumption by 28%. The proposed app have potential for future development, its integration with cloud services to optimize the application, the identification of people if they gave their agree, optimization of routes taking into account accessibility for people with visual impairments, a recognition of banknotes and price tags in stores, and automatic determination of object colors by choosing clothes, products, etc. The proposed solution has both practical and scientific significance, as it aimed at improving the accessibility of the environment for individuals with visual impairments, providing them with tools necessary for independent and effective work with digital technologies. The main advantages of the developed solution include accessibility of digital content and functionality through intelligent object text and scene recognition, and reduced cognitive load through the use of multi-modal interfaces. The developed software model has potential for software advanced, including integration with IoT devices, extension of functionality to support other types of disabilities, adaptation to diverse linguistic and cultural contexts, and application in educational and rehabilitation programs. Thank you for your attention.
Thank you, Lena. Dear colleagues, do you have any questions to speak on?
Можна мені, Василь Чигінь, професор
please.
політехніки. Перше питання ви сказали, пані Олена, так?
Так.
Вітаю. Що система працює локально на пристрої, тобто on-device, зокрема на Raspberry Pi. А оскільки розпізнавання відео і синтез мовлення сильно навантажують процесор, яка у вас виходить сумарна затримка латенції від моменту виявлення небезпеки камерою до того, як незряча людина почує голосове попередження?
Ну, по-перше, ми максимально намагалися зробити наш додаток легким, зокрема використовуючи тайні YOLO моделі більш легкі. І ми вимірювали затримку, але, на жаль, зараз конкретні цифри я навести не можу.
Добре, дякую. І друге питання. Я бачу на вашій схемі, що ви одночасно використовуєте моделі Tiny YOLO для відео та Serent для розпізнавання тексту. Чи не виникає у вас проблеми термального тролінгу, тобто критичного перегрівання процесора, мікрокомп'ютера при такому високому навантаженні в реальному часі? Як ви з цим боретеся?
По-перше, наш Context Engine, відповідний модуль визначав, який зараз використовувати режим, так, щоб одночасно не спрацьовували всі функції. І таким чином зменшували навантаження і на користувача, і на систему.
Зрозумів, дякую. Обмеження таких кадрів і активне охолодження вас, напевно, це дійсно класичні перевірені кроки для стабілізації мікрокомп'ютерів у таких складних кіберфізичних задачах. Я вам бажаю успіхів в далекій Полтаві.
Дякую.
Щастя і здоров'я.
Thank you, Vasil, for your questions. Thank you for your answers. So, our subsection ends. So we have break for 27 minutes, and we will continue at 11. Thank you for your presentations and your questions and answers. See you.
Dear colleagues, let's continue our workshop. Do you hear me?
Yes, we do.
Okay. Dear colleagues, please accept my apologize for not being on camera. I'm having problems with my internet connection today. Maybe it's so hot. I would like to remind you about the timing, 10 minutes for your presentation and about 5 minutes for questions. First presentation, it's supporting its project management decisions using intelligent information approach. Who will be speaker?
Hello everyone, I will be a speaker.
Okay, welcome, Sergey.
Yeah, let me share my screen. Do you see my screen right now?
Yes.
Okay, so hello everyone again. Today I will present our approach in intelligent decision support for personal related decision in IT projects. And the main idea is simple. It is project managers need better support for human related decisions, but they do not need a heavy automated system like that replace their judgment. So our goal is to provide the structured analytic support for better managers' decisions. And modern IT projects usually manage the budget, schedule, and scope with the clear and formal tools. But personal evaluation, team formation, and role assignment are still often based on intuition and informal judgment. So this creates an important problem because personal decisions strongly influence project risks and delivery results. So human complexity is still much less supported than other projects areas. And here we show the missing middle in a project decision support. The traditional agile practices are flexible, but they create high cognitive load and often depend too much on subjective judgment. Heavy enterprise decision support system platform offer advanced analytics, but they need large data repositories, strong integration, and high organizational readiness. And our target is a middle zone. It is like the lightweight, context-aware, intelligent information processing that support the weekly formalized decision in dynamics. So this slide explains our main concept. We do not need a system that makes the decision instead of the managers. We need a system that transforms the unstructured observation into intertable analytics indicators. And in these models, managers' judgment remains responsible for the final interpretation and final choice, while intelligence processing help organize data and reduce the cognitive load. So here we can see our conceptual model. It is the framework. It includes input, feature extraction, normalization, analytics, stabilization, context, reporting, and interpretability. These stages convert the heterogeneous and temporally structured data into the decision-oriented outputs. A very important point is that the interpretability is included directly in the framework because decision makers need to understand how the analytics result was formed. As an applied case, we focused on personal evaluation during the IT team formation. This process is uncertain and quickly formalized, so direct interpretation of role observation can lead the inconvenient decision. So apply this 8-stage framework to video interview data in order to extract the stabilize and take the emotional dynamics. As a result, the system can generate the structured indicators such as the emotional stability, communication clarity, engagement level, and other useful signals. These slides show how the analytics are embedded into the interview process. So the candidate take the part in an online interview, the HR specialist manage the questions and review their reports, and the module process the video in a real time or from the recorded materials. So the key idea is that the analytical components are supported element inside of the this workflow, and they improve the information flow, but they do not like replace the human authority in final decision. Here we can see the internal analytical life cycle. It includes the acquisition, the preprocessing, interface validation, stabilization, and contextual logging, the reporting. At every stage, system noise and external variability are reduced. So this means that the final result is not just some raw technical output, but a cleaner and more reliable analytics trace for the final interpretation. Our system uses two models at the same time: the pre-trained model, like DeepFace, and the custom model, Torch model. So we do this not to get our automatic black box answer, but to create some decision support signals. Comparative output help managers see dominant classification patterns, more clarity, and this approach support interpretation and transparency better than relying on the single PQ score. So one important step is the framework is temporal stabilization. So the raw emotional observation often contain the noise and short-term micro fluctuations. So it will interpret them directly. We may get the base conclusion, and the sliding window like approach smooths these changes over the time and reveals more stable behaviorist patterns. So this gives the stronger basis for the like understanding the information about the candidate during the his evaluation. What about the emotional indicators? It should not be like the analyzed separately from the interview context. In our framework, the system registered the question-related events and content emotional dynamics to the specific triggers. So this allows HR specialists to see how the candidate reacted to the technical questions, like or the stress test scenarios. So the analytics results becomes much more understandable for us and like for final decision making for the manager. Yes, sorry. Okay, I can continue. So the final output is the persistent analytics trace and decision-oriented report for the manager for the HR specialist, and it summarizes the key indicators in a form that they understand that even without the deep technical knowledge, at the same time, it is presents the system keeps intermediate representation and explains how aggregated results were formed. Like we have like the full information about the candidate. And this slide explains the balance between the machine and human roles. The machine handles the feature extraction, normalization, continuous monitoring and stabilization, and contextual alignment. The human is still responsible for the semantic interpretation, the culture fit assessment, the verbal responses analysis, and the final personal decision. In the simple words, it's like the AI provides the map, but the human still drives the car. The same framework can be used in other weekly formalized project scenarios. For example, it can support the team stress monitoring during the difficult sprints, continuous personal risk evaluation, or analysis of communication problems in the distributed teams. So because the framework works with the the dynamic data, it fits well into the agile and hybrid project environment. So its value is not like limited only in the candidate interview. In conclusion, our work addresses in the important hidden risks in a project, personal decision that still lack structured support, and we propose the lightweight and contextual intelligence layer that stand between the informal judgment and the heavy enterprise DSS solution. So the key message is like that intelligent frameworks should improve transparency, aggregate the temporal data, and support managers, but never replace human managerial judgment. Thank you for your attention, and I will be glad to answer to your questions.
Thank you, Serhiy. Dear colleagues, do you have any questions for the speaker?
I have one question, actually two questions. First question is, how many different emotional states detects your service?
As we can see here, we have a different, we have 8 steps, and this every step we have like this emotional parameters using which we can provide some assessment of the candidate.
How many different emotions do you detect? Anger, I saw on another slide.
Sorry, we have anger, fear, happy, natural, and sad.
So 5 emotional states at all. Thank you. And second question is, does your service suggest any decisions to be taken?
Yes, it's like if we will use artificial intelligence for grab information, we have some metrics that help us to make some decision. If we want it provide some information, some propose which candidate will be better, but the final decision it is for manager. But he can use the information provided by this framework and by using AI.
So your service can suggest the best candidate, yes?
Yes.
Okay, thank you.
Thank you. And I have little questions. Serhiy, how reliable are your system's decisions? Are they accurate?
Okay. So we have 2 approaches. The first, we separate the behavior data from the sensitive attributes and do not use those attributes as input parameters. So the second, the system never makes decision automatically. It generates the indicators and explanations while the final decision belongs to the managers, as I said in previous. And the third, we build the possibility to review the continuous cases. We analyze whether the model systematically undervalues or specific groups or behavioral types. So in practice, we treat the model as from the hypothesis assistant rather than automatic judge, if I correctly understand your question.
Okay, thank you. Dear colleagues, are there any more questions? No. Okay, thank you, Serhiy. Next presentation is scheduling method for real-time process in cyber-physical systems based on zero copy. Who will be presenter? Andrei?
It's me, Holvatyuk Andrei.
Welcome.
Can you see my presentation?
Yes.
Yeah, okay. Good morning, everyone. My name is Andrei Holvatyuk, and I am here to present our research titled Scheduling Method for Real-Time Processes in CPS based on Zero Copy. This work was developed by our research team, and today I will be sharing our findings at this workshop. Let us start with a brief introduction. CyberPhysical systems, or CPS, combine physical sensing, computer processing, and mechanical action. In robotics and autonomous system, these actions must happen within very strict time limits. Our work focuses on modular systems built on the ROS2 framework that use mixed hardware where CPUs, GPUs, and FPGAs work together. The core problem we address is that while modular components are easy to reuse, moving data between them requires extra copying and memory transfers. This extra work destroys the predictable timing that real-time systems rely on. The problem becomes clearer when we look at modern hardware. We often distribute computation across CPUs, GPUs, and FPGAs, but integration them while keeping strict real-time constraints is highly complex. Despite its flexibility, the standard ROS2 middleware does not guarantee strict timing for complex data flows. The biggest bottleneck are memory transfers. Moving data between different memory zones and copying it redundantly across the PCI bus creates massive delays, which violates our real-time requirements. This slide shows the baseline architecture of a typical cyber-physical system, which operates as a closed loop. First, physical sensors like cameras, GPS, and LiDARs collect multi-dimensional data. Next, the high-level ROS2 software processes this data in the perception and planning layers to generate safe trajectories. Finally, these plans are sent to a low-level microcontroller acting as the control layer, which transfers the commands into real-time signals for physical actuators like the throttle and steering. To solve the timing and memory bottlenecks, we propose a two-part solution. First, we create a customized ROS2 real-time scheduler designed specifically for task trees, known as directed acyclic graphs, or DJs. This scheduler uses priority-driven processing for main tasks and last-in, first-out queue for child tasks to minimize latency. Second, we introduce zero-copy memory management. This system is aware of different memory domains and allow components to share physical memory without copying the data, ensuring deterministic access. Here you can see how we structured our implementation into interconnected blocks to ensure stability. The control block handles the core logic and state estimation. The real-time task planning block creates the schedulers based on deadline and zero-copy interfaces. The execution block uses the custom ROS2 executor that supports limited task interruption. And finally, the zero-copy memory management block guarantees predictable access by sharing buffers between the software on the CPU and the hardware accelerators. The key technical components of our system rely on a custom ROS executor, running on a Linux system with a patch which ensure predictable CPU operations. For data sharing, we built a specialized memory allocator integrated with the Data Distribution Service, or DDS, to allow true zero-copy data flow. To connect the hardware accelerators instantly, we use Spinach shared memory for GPUs and DMA buffers for FPGAs. We tested our proposed method under high load using complex scenarios that includes sensory, computational, and control tasks. The results were highly successful. Our zero-copy DAG-oriented method greatly outperformed traditional scheduling methods. By bypassing standard data copying to the hardware accelerators, our system almost completely eliminates missed deadlines and memory fragmentation, which is vital for safety-critical operations. Looking at the specific number, our method achieved up to a 60% reduction in average latency and 80% reduction in response time jitter. Memory overhead was reduced by up to 50%, and we successfully eliminates all of redundant data copying. This performance gains means that the system is highly predictable under heavy loads, which directly improves control stability. In conclusion, our experiment proves that control logic, task scheduling, and memory management must be designed together as one unified framework. This unification provides superior control quality by minimizing errors and reciting external physical disturbances. Furthermore, this fast low latency framework provides the exact performance needed for advanced cybersecurity features such as a real-time polymorphic botnet detection system. Ultimately, our solution is highly practical for scaling hardware-accelerated autonomous deployments in industrial and robotic environments. Thank you for your attention.
Thank you, Andrei. Dear colleagues, do you have any questions for the speaker? Alexei, maybe?
Yes, I have a question. Are there any drawbacks of your solution? For example, lower reliability and things like that?
One more time, please.
Your solution, are there any drawbacks, negative aspects of your solution? Because you pay something for...
When we tested, we can't find this, but I think it's a need for more research, and I think we find it, but not now. Now we can find it.
I think that with the zero copy, you lower reliability, because zero copy is essentially you allow any process to access memory of any other process. So reliability in this system is lower. That's main disadvantage of your solution. And the second question, did you compare your solution with the schedulers from real-time operating systems?
Yeah, we compare with some of them, and our solution gain us better speed of work, and I think it was a main goal of our research, to increase the time needed system to do operations.
Thank you.
Dear colleagues, are there any more questions? No questions? Okay, thank you, Andrei. Next presentation is methods of avoiding interlocks of tasks in distributed systems based on inter-process interaction protocol. Who is speaker?
I'll be the speaker.
Alexander. Okay, welcome.
Yeah, give me a second. Do you see the screen?
Yeah.
Okay, cool. Good afternoon, dear colleagues. My name is Alexander Martsenko, and I will present our work titled Methods of Avoiding Interlocks of Tasks in Distributed Systems based on Inter-Process Interaction Protocol. The central problem of the presentation is how to organize interaction between distributed tasks so that the system does not enter a cyclic waiting state. I will begin with the motivation. Distributed and parallel systems help us increase performance by executing many tasks at the same time. However, parallel execution also creates coordination problems. A task may wait for a message, a resource, or a result from another task. If several tasks wait for each other in a cycle, the whole workflow can stop. This is what we call an interlock or a deadlock-like blocking state. In monitoring and cyber-physical systems, such delays are especially dangerous because they may postpone detection or decision-making. The goal of our research is to avoid unsafe waiting states before they actually form, so the focus is prevention, not only detection after failure. Our contribution consists of three connected parts. First, we use structural model of task dependencies. Second, we organize execution through reactors and inter-process interaction protocol. Third, we evaluate both correctness and performance using a set of practical metrics. Together, these parts form a coordination method for distributed system. The proposed model separates two different views of the system. The first view is the dependency graph. Its nodes are tasks, and directed edges show that one task depends on another. The second view appears during runtime. It is resource wait graph, where we can see which reactor or process is waiting for which response on resource. Even if the original dependency graph is acyclic, the runtime graph may still contain a cycle. Therefore, avoiding interlocks requires control over both the task structure and the runtime interaction. This slide summarizes the method in simple sequence. First, we build a task graph that represents dependencies between two operations. Then we assign graph nodes to reactors in controlled way, taking the longer and more critical paths into account. After that, requests between reactors are processed through the IPC protocol. The protocol checks whether a new request may create unsafe waiting. If the request is safe, it is executed. If it's risky, it can be delayed, reordered, or redirected. In this way, the method avoids the formation of cyclic waitings. A key part of the method is reactor allocation. The main idea is simple. If a node belongs to several paths, priority is given to the longer path. This protects the critical path from being concentrated in one execution environment. The allocation is performed in two phases. First, graph paths and traversed and their lengths are collected. Second, each node is assigned to a reactor associated with the longest relevant path. This helps preserve the non-distribution invariant and prevents artificial bottlenecks in the execution graphs. The second key part is inter-process interaction protocol. Reactor allocation controls the structure, but runtime messages can still create blockings, even if they're synchronous or badly ordered. Therefore, the protocol regulates how reactors send requests, receive responses, and release resources. The main rule is to avoid mutual synchronous waiting. In practice, this can be supported by asynchronous request response, one-way messages, non-blocking calls, timeouts, and ordering rules for resource access. To evaluate the method, we consider correctness and performance together. Correctness is represented by the probability of interlock or cyclic waiting. Performance is represented by execution time and throughput. We also measure coordination overhead because an avoidance method should not become too expensive. In addition, waiting time, resource holding, dependency chain length, and blocking risks will help the system decide whether a request should be executed immediately or postponed. The experimental results show that the developed method reduces probability of interlock to 0.002. For comparison, classical detection gives a higher value and execution without avoidance is worse. At the same time, the method keeps coordination costs controlled. The average execution time is 5.2 seconds, throughput reaches 45.6 units, and overhead remains at 6.7%. These results show that avoiding interlocks at the coordination level can improve reliability without causing excessive performance loss. To conclude, the main message of the work is that interlock avoidance should be treated as a coordination problem. It's not enough to detect blocking after it has appeared. The proposed method combines three elements: structural task allocation, protocol level control of inter-process interactions, and runtime metrics. This combination helps preserve progress in distributed systems and can be further adapted to heterogeneous computing environments and distributed monitoring pipelines. Thank you for your attention, and I will be happy to answer your questions.
Thank you, Alexander. Dear colleagues, do you have questions? Okay, I have a question. What are the advantages and disadvantages of your approach?
Our approach, the advantages of our approach is avoidance and prediction of interlocks, meaning we do not spend time on fixing interlocks that has already happened in runtime. That meaning we do not spend additional time on it. One of the limitations would be that it requires knowledge of its dependencies, meaning for highly dependent system, the dependency graph may need to be regularly updated in runtime, which will create additional overhead.
Okay, thank you. Are there any more questions? No. Okay, thank you, Alexander.
Thank you as well.
Next, our presentation is automatic hardware synthesis approaches for AI-driven self-configurable computing in edge systems. Who is speaker? Victor?
Yes. Good afternoon. Can you hear
Welcome.
me?
Yeah. Hear and see.
That's good. Just a moment, I will share my screen.
Okay.
So this is the presentation I would like to share with this topic. We are three authors. Anatoly Melnik, representing two institutions. This is Intron Limited, IT Step University from Lviv, Ukraine. Me, Viktor Melnik, representing also two institutions. One is Catholic University of Lublin from Poland and Lviv Polytechnic National University, and Dr. Fazal Rahman from QLoud Technologies from Estonia. We devoted this report to very promising direction of development of the artificial intelligence driven systems. So these are self-configurable computing systems in edges, or self-configurable computing in edge systems. The agenda for the report is following that. We will discuss short overview. We will make introduction, motivation. Then the main challenge that is here shown in this report, the requirements for the synthesis tools, classification and overview of them, and comparative analysis. Finally, we will see the case study of one of the tools. This is Chameleon, a so-called Chameleon C2HDL tool from Intron Innovations, and some experimental results for fast Fourier transformation processor synthesis. And we will conclude the results. So firstly, there is a system demands that are very important and actual today in edge AI and cyber-physical systems. There is a growing need for high-performance, energy-efficient, configurable platforms. Such platforms can be implemented in the way of field programmable gate arrays, which ensure dynamic adaptation to the changing workloads, the latency constraints in real time, and they also require very high resource efficiency in order to balance power, latency, and flexibility according to the design objectives. There is a critical challenge in such a systems which is envisioned. This is efficient automatic hardware synthesis. What means automatic hardware synthesis? This is transforming the algorithmic description into optimized specialized processors, which will be executing respected workloads. There must be a need to eliminate the RTL design effort, ensure functional completeness in order to be able to execute arbitrary tasks, and optimized architectural mapping. In this research, we define the automatic hardware synthesis, the requirements for automatic hardware synthesis tools. We propose the classifications of these approaches. We provide their comparative evaluation and make the case study. The primary finding of the approach is that one of the classes, this is high-level language to hardware description language approach, provides a highest functional completeness and adaptability for the self-configurable edge computing. So we see the shift to edge AI today, and we know that the general purpose processor cannot balance latency, energy, and performance as at a high level. So this is the reason that we observe the dominance of the heterogeneous architectures, which are empowered with graphic processing units, with neural processing units, and FPGAs in modern edge analytics. We know that the FPGA provides massive parallelism, dynamic reconfiguration, which ensures also adaptation to changing workloads at runtime. Sometimes we can also see this dynamic partial reconfiguration of FPGA, and it provides also high ratio of performance to power consumption. In self-configurable computing, there is a need to provide automatic synthesis of specialized processors. The traditional approaches, like the traditional RTL design, is very slow, and it also requires expertise. So there is a need to transform the algorithmic description into optimized hardware models. In the future systems, which will be AI-driven, as we can see, self-configurable FPGA-based ACE computing, there is a need for low latency, high energy efficiency, and dynamic hardware adaptation. So for that reason, we use FPGA, and for example, the application would be the AI inference engines, tensor, adaptive CNN accelerators, etc. So the challenge, as I already mentioned, that there is a need for efficient automatic hardware synthesis, which is, according to conventional methods, it's not automatic. There is a class of tools which are called automatic hardware synthesis tools, which are targeted to transform these descriptions into hardware architectures. And several classes of these tools are, firstly, library-based generation, the reusable component-based generation, the configurable processor architectures, high-level synthesis methodologies, and the last is multi-level intermediate representation and circuit intermediate representation-based design flows. So the goal of the research is to investigate the requirements which are imposed to these tools in the AI-driven self-configurable FPGA-based edge computing and perform the analysis of these approaches in this context. What are the requirements for the synthesis tools which are imposed by the systems of edge computing? These are functional completeness, FPGA architecture awareness, interface awareness, and performance and resource efficiency, and runtime adaptability and AI-oriented optimization. We provided a deep analysis of these requirements, and we find out that what means functional completeness, that it is the ability of the tool to automatically generate the specialized processors from arbitrary high-level algorithm description while preserving the required functionality, computational semantics, and implementation constraints. So the tools mostly are functionally limited, but we can also divide them by classify them as functionally complete or functionally complete with the class of algorithmic features, functionally complete within the class of problems, and the tools with limited functionality. The FPGA architecture awareness means that while we can generate the hardware descriptions, we can take into account the structure of the devices, of the platform of edge nodes, which deploy the field programmable gate arrays. Which requirements this are? This is efficient utilization of the FPGA resources, considering routing complexity, placement constraints, support for partial dynamic reconfiguration, support for automatic parallelization of algorithms, scalable hardware generation, and optimization for system features like timing closures, pipeline balancing, etc. In context of interface awareness, most important that these tools have to automatically generate not only just hardware alone, but also with computational hardware interfaces. And in this context, the capabilities should be automatic generation and integration of interfaces, the generations of interfaces which are compatible with used FPGA standards like XCI, PCI Express, etc. Support for dynamic interface adaptation and flexible generation of such architectures. In context of performance and resource efficiency, these tools have to provide optimization regarding that characteristics, and the capabilities are very interesting. Sometimes they may look contradictory. For example, we may expect high performance, but from another hand, we would like to have also low power consumption. So some contradictory requirements may be used in order to as a constraints for the automatic synthesis. What are the capabilities for such tools in this context? The architectures has to achieve maximum performance in the constrained devices. It is also balancing resource utilization. It is also maximization of resource utilization within the region when we use hardware, when we use partial FPGA approach. Also, this is a pipelining, the loop unrolling, parallel execution scheduling, optimization of logic for DSP, for clock frequency, memory, and so on and so on. Related to runtime adaptability and AI orientation. So this is something new related to this tools and new requirements, because this is only emerged in the context of AI computing, AI-enabled computing, yes. And these are support for generation of architectures optimized for machine learning, inference, data flow-oriented computation, runtime adaptability, support for partial dynamic reconfiguration, support for optimization techniques, for example, related to reduced precision arithmetic, adaptive voltage, etc. So we have classified the synthesis approaches, and we identified 5 main classes. These are library-based generation, component-based generation, of course, configurability-based generation, high-level synthesis and high-level language to hardware description language synthesis approaches, and mentioned multi-level intermediate representation and circuit intermediate representation based and AI-assisted high-level synthesis approaches. These approaches are different because some of them are quite old, historical, some of them are new, and they differ in terms of different requirements which were discussed. Very shortly, the overview of the approaches. One of the earliest method is a library-based generation. How it looks like that we have the set of processor models, and we have them prepared, predefined, and the question is just to take in as an input the configuration parameters to select one which is suitable for that parameters and take the files of this model to the output. This is the principle of the operation of such tools. These tools are very, I would say, basic and very easy to implement. Some examples we see, this are Logic Core from Xilinx, Mega Core components from Altera, Open Core projects, etc. The advantages is short generation time, the high implementation reliability, but there are very big limitations. The functionality of such tools are very restricted because these are restricted by the set of the modules which we have in the libraries. Some extension of that approach is provided by component-based generation when we have not a full IP core in the library, but just a component of them. And on the base of that component, we can construct the IP cores, processors description, which are suitable to the input configuration parameters. For that reason, we should have some additional software which would automatically generate the top-level description files and provide them to the output. This is like some improvement of the previous technique, but anyway, it still is limited functionality and provide limited functional completeness. The configurability-based generation means that we may have the configurable processor description, which is adjusted according to the configuration parameters used. Many examples of such approach we may find. Usually, this is implemented using the hardware description languages mechanisms like generate, like using of generics, etc. in VHDL, for example. The new generation of the tools provides conversion from the high-level language, like, for example, C or C++ or System C, OpenCL, or some other, to hardware description language. These tools sometimes are based on some configurable architecture template. Sometimes they are just translating the description from high-level form to hardware description. Also, it supports constraints in terms of performance, latency, equipment, etc. And input is high-level description. The output is sometimes it is the hardware description description language code. Sometimes it is a configuration code for the FPGA. We have many representative examples, historical and contemporary, as we can see here. These tools have advantages. There is a high degree of functional completeness because it's not constrained by the set of the modules in the library, for example, because it may be constrained some high-level language constructs, but anyway, we may program anything in the high-level language. There is a limitation. Limitation is following that synthesis quality depends on optimization directives, the algorithmic structure, memory access patterns sometimes, and some other factors. The algorithm is one of the most, I would say, important limitation here. The algorithm itself. The last generation of such systems are based on multi-level intermediate representation, when we have some hierarchy of the representations. On each of the layer of that hierarchy, the system may have may perform automatic manipulation and optimizations. The transformation process is following that we have the high-level algorithmic description on the input, which is then translated or converted to the intermediate representation on the high level. Then we have the data flow-oriented representation, the hardware-oriented representation, and finally we have the RTL description of the model, which we may further synthesize, of course. The advantages of this kind of tools, this is again substantially improved support for scalability, partial dynamic reconfiguration, runtime specialization, which increases of level of hardware adaptability. This is compatibility with modern compilers, for example, which are AI oriented, for example, TensorFlow, PyTorch, etc. What makes them suitable for appropriate edge applications. And this is incorporating machine learning techniques like reinforcement learning and others, which makes them, again, suitable for intelligent optimization of hardware architectures under multiple constraints. We perform the comparative analysis of these approaches according to 8 criteria which were identified previously. These are functional completeness, FPGA architecture awareness, and others: interface, automatic parallelization capability, runtime adaptability support, the suitability for AI-oriented and edge computing, resource efficiency optimization, and scalability. The results of comparison is given here in the table. This is classified from the limited to low, medium, and high. And as a result of comparison, we identified we made following implications: that library-based and component-based approaches are still effective for implementation in specialized domain-oriented accelerators, with relatively stable computational structures. It still are very high efficient in terms of FPGA resource usage. But they suffer from insufficient adaptability and limited functional completeness. The same or similarly, it is related to configurability-based approaches, which are a little bit better in terms of adaptability because they are programmable. They are mostly suitable for embedded heterogeneous systems. But we see that the last two classes, these are high-level language to HDL and multi-level intermediate representation approaches. They are demonstrating highest functional completeness, strong scalability support, FPGA architecture awareness, and extended suitability for adaptive edge AI systems. Moreover, we have identified very clear technological evolution trajectory from the library-based synthesis to component-based to configurability-based. HLL to HDL synthesis, and multi-level approaches. Finally, we have the AI-assisted adaptive synthesis approach, which is even more efficient. And as a case study, we have taken the Intron Chameleon C2HDL tool. This tool provides automatic synthesis of the processor description from the C language, ANSI C language, and it generates the output project according to the predefined architecture. There are a set of multiple functional units which are parallel. There is a shared memory. And the output is the set of modules which are fully customized for the given workload in terms of the number of these functional units, in terms of the functionality of each of them, because each unit may perform different operations and operations which are defined by the high-level description. And we obtain the VHDL code in the output and the configuration file in the for the ROM memory. As a case study, we performed the experimentation on generation of fast Fourier transform processor. We have generated the set of such processors with different number of LUs. Depending on the workload, we may change this number. Our question was, for example, to provide to ensure the scalability of this design to see how long it takes to synthesize. So we see the synthesis time, for example, for one LU module is about 1 minute. This is on the platform with Intel 3.1 gigahertz CPU. So 1 minute, a little bit more, yes, and 2 LUs is 1.7 minutes, 16 LUs is 2.4 minutes, and 50 LUs is 3.5 minutes time taken just for generation of this modules. There are some also results of evaluation of the generated processors in terms of data latency and frequency they may provide. As a conclusion, so we in this research we proposed.
Victor, was
Yes.
very interesting presentation. Dear colleagues, do you have any questions for the presentation, for the speaker?
Can I ask one question?
Yes.
Okay, please.
Good day. Modern FPGAs have very many different hard cores inside. How do you consider existence of different hard cores in different FPGA families, in Xilinx families and different in Altera families?
Thank you for question. So such a set of features for each edge node has to be individually on the level of its operation, like in the software level, has to be provided separately for each node. So each node has to it operates according to some set of software, yes, some algorithm. So the algorithm has to be fulfilled, of course, not algorithm, but this software has to be fulfilled by the descriptions of what is inside, how to use it with some constraints, etc. Additional directives.
Thank you.
Thank you. Are there any more questions? No? Okay, thank you, Victor.
Thank you.
Colleagues, I would like to remind you of the timing, please. 10 minutes for your report. And colleagues asked for the presentation to be brought forward. Does anyone have any objection? No, okay. Thank you. Next presentation is a distributed intelligence system for spectral analysis and real-time bioacoustic signal monitoring. Please, who is speaker?
Василь Чинь, так?
Так, так.
Так, добрий день. Dear colleagues, since this is highly specialized technical
Please
topic, as for me,
presentation, please.
Stop share. Ага.
It's not presentation.
One moment. Так.
Maybe it's your presentation.
Do you see my робочий стіл? Yes?
Yeah.
Good?
We see you.
Good?
Yeah. Let's start, please.
Ага. Я попробую все-таки українською мовою і навіть дуже так швидко темпом, тому що дуже ми спішимо. У нас тут сталося.
Я розумію.
Excuse me, the language of workshop is English.
Yeah.
Чи ви мені дозволите українською мовою і буде паралельна трансляція? Мене чути?
I'm sorry, but unfortunately, it's English. It's language in our workshop. Please try to present it in English. Your presentation.
My presentation is double form. Okay. Distributed intelligence system for spectral analysis and real-time bioacoustic signal monitoring. Василь, Doctor Science Polytechnic, and Hanna Шиковska, Doctor Medicine. Introduction. Importance. Real-time bioacoustic monitoring is crucial for early medical diagnostic. Challenge. Processing complex sound signal in distributed computing network requires high efficiency. Our solution, intelligent hardware software system that performs fast spectral analysis. Aim and objectives. Research aim to design distributed intelligent hardware software system for continuous real-time bioacoustic monitoring. Main object to overcome data transmission latency and analysis limitation of existing digital stethoscope. To implement a low latency FFT algorithm using property our own software. To integrate edge computing node, Raspberry Pi 4, with secure cloud data streaming. Hardware configuration. We have two schemes. First, it is budget external schemes based on sensor max ES condenser microphone model. This is here. Hardware configuration schema to be a high precision technical complex, high sensitivity clip microphone, CLIP XLR, and specific soundproof on-body capsule, audio interface, focus Scarlett Solo with 48 phantom power, and digitalization parameter. Do you see? Software mathematical processing. Property software suite we have on written in micro Python, C++ and Python, low-level Node, PyCo, and high-level analytical Raspberry Pi 3. Fast for transform algorithm for time frequency domain transition. Spectral lake reduction application of the HAM window function to each data frame. Experimental result of schema A. Signal to noise is too high, 31% to total signal levels. Signal characteristic ratio of noise to use full signal is high. Average noise is 8 units for 26 units of the first peak. Main limitation, fine structure of the head pulsation is blurred and low detail due to the hardware noise floor. Experimental results for schema B. Signal to noise ratio, as you see, is high level noise amplitude is reduced down to 1 and lower signal level. Signal characteristics superior clarified achieved. Average noise amplitude of 50 units for 5,000 units of the first peak. Main advantage, high precision separation, precise identification, and detailed analysis of head sound dynamics. Conclusion. Developed system, distributed intelligent hardware software complex for real-time bioacoustic monitoring has been successfully created. Hardware validation, schema B, with high precision digitalization ensure maximum noise immunity required for medical diagnostics. Software efficiency, proprietary software provides stable low latency FFT analysis and reliable data streaming to edge nodes. Medical impact, the system enable highly detailed and continuously monitoring of the fine heard sound dynamic. Patent protection of our development. Legal protection, scientific novelty, and technical solution of the developed complex are officially protected by State Intellectual Property Service of Ukraine, patent number in 2025, and Ukraine, and second one, it is hardware architecture developer for bioacoustic device, and second, connected with method for the distributed spectral analysis. Practical status. Availability of protective documents confirms the author's global priority and the full readiness of the technology of commercial implementation.
Thank you for your presentation.
For your attention. Thank you.
Thank you for your presentation. Colleagues, do you have any questions for the speaker? Are there any questions? Okay, I have a little question. Is your system scalable for more sensors?
My system, once more, please. My system is... Your question once more, please.
Чи передбачене масштабування вашої системи зі зростанням датчиків?
Так. Yes. Я можу все-таки українською, мені легше, вибачте, швидше не підготовлюся, вже давно не був на конференції. Отже, система зараз просто масштабується. Так, фірма, одна з медичних фірм, яка зв'язана з електронікою, взялася за масштабування. Це і вперше система, яка буде моніторити, вона дуже маленька, вона буквально поміщається в кишеню або навіть на тіло з сучасними мікросхемами. Таким чином, звуки серця, не тільки серця, легень, там інших, так сказати, капілярів і так далі, можна буде записувати, вивчати. Медики в цьому зацікавлені кровно. Дякую вам.
Thank you for your answers. Are there any more questions, colleagues? No? Thank you.
Thank you very much. Goodbye. Nice of you.
Thank you. Bye. Next presentation is auditable decision-making in intelligent cyber-physical systems using semantic transition and role sets. Please, Pavlo, yeah.
Dear Elizaveta Hennadina, thank you very much for opportunity to give a speech. I would like to ask the previous speaker to end the presentation because I'm not able to present. So the slides can be visible, I hope, right now. And I can start.
Yeah.
All right. Okay, so once again, good day, and thank you for joining the session. On behalf of my colleagues, I would like to present our work on auditable decision-making in intelligent cyber-physical systems using semantic transition and rough sets. The central idea here is to make deep learning-based control systems more transparent by translating opaque neural representations into explicit symbolic rules. The presentation is organized into 4 parts. First, I will motivate the need for auditable reasoning in safety-critical cyber-physical systems. Then I will introduce the SAMTRA method, discuss the main experimental results, and conclude with implications, limitations, and future work. Modern cyber-physical systems increasingly rely on deep neural controllers, but these controllers remain difficult to inspect. Local explanation tools can highlight parts of an input, yet they do not provide reusable global decision logic. Our goal is to convert latent neural features into explicit, conflict-aware symbolic rules without retraining the original controller. The framework makes 3 main contributions that we propose during our study. First, a linear transition matrix maps compressed neural representations into interpretable semantic attributes. Second, weighted entropy density discretization, or just VEDD, converts continuous semantic signals into robust symbolic states. Third, rough set induction produces a global rulebook that clearly identified conflicts, boundary regions, and abstention. Existing explainability methods provide useful inspection tools, including silencing maps, concept bottlenecks, decision trees, and rule learners. However, they often lack a discrete symbolic layer that supports global logical reasoning. In our case, SAMTRA addresses this gap by connecting neural features to cyber-physical systems, relevant semantics, and by allowing the system to abstain when evidence is contradictory. SAMTRA operates as a 2-stage post-hoc audit layer placed on top of a frozen neural feature extractor. The first stage maps latent neural representations into semantic attributes. The second stage granulates these attributes into symbolic states and induces a rulebook. The final output is not only a prediction, but an auditable trace of the reasoning process. In the first phase, SAMTRA learns a rich regression transition operator from latent features to semantic attributes. This matrix is auditable because each weight connects neural evidence to a specific semantic variable. Importantly, the underlying controller remains unchanged, so the method can be applied to already trained systems. The next step is to convert continuous semantic attributes into symbolic states. VEDD does this by balancing entropy reduction with a local density estimate from kernel density estimation. As a result, thresholds are placed in sparse semantic regions, making symbolic states less sensitive to small perturbations or some sensor noise, as usually happen in cyber-physical systems. After discretization, SAMTRA applies rough set granulation to identify reliable semantic patterns. objects with identical symbolic signatures but different classes from boundary regions. The lower approximation induces dependable production rules, while minimal reducts preserve the rulebook's logic using fewer attributes. During inference, SAMTRA does not force a decision in every case. If activated rules disagree, the system usually marks a conflict. If no reliable rule applies, it abstains. This honest silence mechanism is especially important for cyber-physical systems where uncertainty should trigger a fail-safe response or human review rather than an overconfident reaction, as it usually happens with neural networks. The first experiment evaluates how accurately the transition matrix reconstructs semantic attributes on the benchmark dataset called Animals with Attributes version 2. Across 5 seeds, the test mean absolute error is 0.1029 and the mean semantic correlation is 0.8070. These values show that the learned transition provide a stable bridge from latent neural features to semantic space. The induced rulebook contains about 59 rules with roughly 4 conditions per rule, making it compact enough for human inspection. SAMTRA covers roughly 84.80% of test instances, while frankly reporting abstentions and conflicts. The cover fidelity score of 40.48% quantifies the audit tags. The portion of neural behavior preserved as strict, interpretable predicates. The synthetic stress test evaluates whether the symbolic layer remains stable under semantic noise. Even at the highest noise level, with sigma equal to 0.20, macro F1 remains relatively high, with approximately 0.80%, and coverage remains 95.2%. This indicates that the proposed VEDD filters small perturbations while preserving the integrity of rule-based interface. Rule-based inference. The rule examples show how SAMTRA turns model behavior into inspectable conditions. For instance, the tiger, antelope, and zebra rules combine semantic states such as pose, hunter, hooves, jungle, and yellow with clear numeric bounds. These bounds allow engineers to compare learned logic against domain expectations or sensor specifications. The diagnostic plots reveal which semantic attributes most strongly influence the transition process and which attributes are reconstructed less accurately. High salience attributes such as pose and vegetation indicate where the model places substantial semantic emphasis. This information helps auditors detect both dominant reasoning patterns and potential blind spots. The threshold dashboard, as presented in Figure 4, shows how operational behavior changes as the minimum rule confidence varies. Lower thresholds increase autonomous coverage, while higher thresholds increase abstention and therefore stricter oversight. This makes the audit layer tunable for different safety requirements, for instance, from permissive deployment to conservative human supervised operation. The inference traces show how individual decisions are explained. A correct case identifies the matched rule, its support, confidence, and antecedent states. An abstention or fallback error can then be analyzed as a boundary case, missing rule, or conflict in the knowledge base, which makes debugging more systematic. Our contribution can be understood as a symbolic digital twin of neural model logic. It makes conflicts and abstentions explicit, turning them into operational signals for halting, fallback behavior, or human review. Because the framework operates post hoc on frozen feature extractors, it can retrofit legacy neural controllers without expensive retraining. So it should be taken into account that the whole contribution works as a post hoc, which means it can be applied to already trained neural networks. The current framework still depends on static, manually annotated semantic dictionaries. It should be viewed as a diagnostic audit layer, not as a full replacement of the neural model, evidently. Future work will focus on automated concept discovery, dynamic attribute space construction, and perhaps large language models assisted generation of semantic representations for changing industrial environments. Moreover, our future work is devoted to validating the center framework on several critical domains, such as medical data, for example, electrocardiography, magnetic reasoning inferences like MRI images, etc. So this concludes the presentation. Thank you for your attention, dear colleagues, and I welcome your questions or discussion about the method, results, possible applications in further intelligent cyber-physical systems. Thank you very much.
Thank you, Pavlo. Dear colleagues, questions, please?
I have one question, if you may.
Yeah.
Pavlo, thank you, first of all, for interesting work and presentation. Could you please tell us to which cyber-physical systems is your approach applicable? Because the data set, the training data set that you used in this work was about animals.
I sincerely appreciate your question. Indeed, the benchmark data said that the contribution was validated at first stage is animals, because it's a great benchmark data set for such tasks as it contains clear contributions. As for specific cyber-physical systems, I would specify those that have sensors with visual data. For example, something related to smart cities that can be connected to CCTV cameras, for example, and make video observations in real time. So that video data will go to the neural network controller, resolve some tasks, for example, object detection, and then this controller that we present here, SAMTRA, can be applied as a post hoc layer to interpret whether the detected objects on the CCTV cameras are those that the neural network really shows, or maybe some mistakes were produced, something like that.
Thank you so much for the answer.
Thank you. Are there any more questions? No. I have a little questions. What are the limitations of your approach?
Thank you very much for the question. So first of all, it's a dependency on static and manually annotated semantic dictionaries, because we deeply depend on the attributes. It is not difficult. It is not easy to provide interpretations using SAMTRA for everything that we would like to have. So if a person understands what is happening on the image or on the piece of data, Samtra can use it as well. If only humans cannot provide clear, explicit dictionaries of how the objects on the piece of data can be splitted into evident attributes, Samtra becomes not as useful as we would like to have. So to make it short, probably the main limitations is the lack of clear attributes.
Thank you.
Thank you.
Okay, thank you, Pavlo.
Mm-hmm.
And finally, its topic is analysis of person recognition errors in a cyber-physical computer vision system. Who is speaker? Olga?
Yeah, that's me.
Okay.
Can you see my screen?
Yeah.
Dear colleagues, first of all, thank you so much for the opportunity to present our work here. And today, on behalf of my team, I will be presenting the topic analysis of person recognition errors in cyber-physical computer vision systems. To start with to start with, computer vision systems have achieved remarkable progress in recent years thanks to deep learning. However, reliable person detection in real industrial environments, such as open-air construction sites or warehouses or parking lots with large area, is still a challenging task. Detection accuracy can be affected by changing lighting conditions, occlusions, complex backgrounds, and a difference between the training data and real deployment conditions, which is shown as a domain shift. To start with, I would like to comment on the motivation on this work. We started on our previous research where we worked on the experimental setup and the method of post-processing video surveillance systems alarm signals using the YOLO neural network. And on the picture from the experimental setup, we can see the examples of image recognition error. First of all, I would like to pay attention to different objects that are recognized wrongly. We can see a lot of false positive results where the industrial objects are recognized with errors, and also we can see the errors of human recognition. In our previous work, as I previously mentioned, we mostly focused on the object recognition. And in this work, to continue the previous research, we decided to focus more on human recognition because to illustrate this problem, we present a real-world example from the previous research. During testing, the model incorrectly detected a stack of industrial pipes as a person with a confidence score of 81%, which is really high. This false positive demonstrates that modern object detection models can still be confused by industrial objects that visually resemble the shape of a human. To better understand the failures, we proposed an error taxonomy that classifies recognition errors into 3 categories. The first category is perception errors, which include problems related to sensors, image quality, lighting conditions, and occlusions. The second category is processing errors, which are caused by algorithm limitations, inappropriate model selection, or hardware constraints. And finally, system errors include communication delays, synchronization problem, and data transmission failures that may affect overall performance of CyberPhysical system. It is difficult to focus on all three categories. So in this research, we decided to focus on the processing errors, such as wrong algorithm choice, because in our opinion, it might have caused such high percentage of false positive that was shown on the previous slide. To evaluate, this graph represents the examples of errors of three types that I mentioned previously. And we conducted the analysis of examples of these errors and the proposals or the methods how to reduce or how to mitigate these errors. The graph is shown on this slide. And as I previously mentioned, we focus on one category, that is processing errors, and we decided to conduct the experiment and try to prove that inappropriate model selection can cause the big error, and we decided to switch the model from YOLO V8S to M model, and the experimental setup, the experimental results clearly showed that model M achieved better performance. It produced lower training and validation losses, higher MAP 50, so precision also was improved, and recall and F1 score. These results indicate that the model detects people more accurate. Model M detects people more accurately and reduced the number of false positives. Here we can see the results of performance, training and validation performance. We tested both models, and here we can see that model M showed a better metrics on performance. We also tested both models using images from known and previously unseen cameras. Although model M significantly reduced the error rate on both datasets, the performance on unknown cameras remained noticeably lower. And this confirms that domain shift is still one of the major challenges when deploying computer vision systems in real industrial environments. In conclusion, our experiments demonstrate that model M of YOLO V8 model provides the best balance between accuracy and robustness among the evaluated models. However, false positive causes by industrial infrastructures are still present. Therefore, our future work will focus on expanding the training datasets with additional background and negative examples, optimizing confidence thresholds, and applying post-processing techniques to improve system reliability. Thank you so much for your attention. I will be glad to answer the questions, if any.
Thank you, Olga. Colleagues, do you have questions? Please, below.
Yeah, thank you very much. Thank you, Ola, for a great presentation. I would like to clarify one thing. How does the study or the system in particular within your study distinguish between false positives that you specified and false negatives in person recognition? And from your results, which type of error is more dangerous for the target cyber-physical systems?
Thank you so much for the question. Actually, we aim to work on all the errors type. I will start from the answer to this question because it is really interesting to study, to investigate what can cause different types of errors on these models. And also we would like to conduct the experiments using different models and also so-called ensemble approaches which combine different models. So this is just like was the start, and we would like to investigate this topic deeply. And as for the question to false positive and false negative, I didn't highlight the matrix here, but actually, as for the causes of main errors, we highlighted the false positive metric that affected the most, that was the most prominent, that caused this error of recognition. So we in this study we focused most on false positive metric, but in next studies I think we will investigate all the error types and try to develop the methodology of how to mitigate such errors in general.
Understood. Thank you.
Thank you so much.
Thank you. Are there any more questions? Okay, I have a little question. Why YOLO model was chosen for the experimental setup?
Thank you so much for the question. Good question. Actually, the YOLO model was chosen because it is actually the simplest one to conduct the experiments. Actually, it is not like the model that gives the best results, maybe, which was shown on the slides, that the model gives the errors, but it was the simplest model to start experimenting with. As I previously mentioned in the answer to the previous question, in our next studies, we will try to combine different approaches, different models that perhaps will give better results. But in this case, YOLO was chosen for the experiments. Thank you.
Thank you, Olga. Okay, I understand that's all for today. Sergey Lysenko, do you have a short break before close ceremony?
Yeah, sure. We will have about 20 minutes and we will meet in 30. See you.
Okay. We will meet after 15, yeah, or 20 minutes break, yeah? Okay.
Dear colleagues, I'd like to start our close ceremony session. And first of all, I'd like to show you that we have prepared three categories of certificates. Yes, and it's a speaker certificate. It looks like this one. Yes. The next one is a certificate devoted to most active participant, and this year it's Alexei Bochkarov. Applause. And Pavlo Vadyuk. Applause. Also, we admitted 3 best papers, and award certificate is certified that Olena Haitan submitted the best paper, as well as Sergei Trevoho and Viktor Melnik. Applause to all authors of papers. Actually, we will send you the link with all certificates to all participants who was presented at the workshop. And my colleagues, I'd like to say that we have witnessed outstanding presentation, interesting discussion, and we explored new direction in intelligent systems, cyber-physical system, artificial intelligence, Internet of Things, computer engineering, and many interesting researches today. Holding an international scientific workshop in Ukraine during wartime, it's a meaningful achievement. It demonstrates that science continues to unite people across borders, even in our difficult situation. My special thanks to our keynote speakers, presenters, reviewers. I'd like to make thanks to our program committee and all people who make it possible to evaluate this workshop. Finally, I'd like to express my deepest gratitude to Ukrainian Armed Forces. Their courage, resilience makes it possible to be here in safe. So, we look forward to welcome you again in the next international workshop on intelligent and cyber-physical system. See you next year. Okay, and maybe Elizaveta, Olha, maybe somebody present like to make some words, please.
May I?
Yes, sure.
Dear colleagues, it was very fruitful workshop. We shared our ideas, our experience, and our scientific approaches to innovative cyber-physical systems, to our maybe novel systems, and it was really a great pleasure to listen to all the speeches. They were all of high level, scientific level, and practical level. So thank you so much for your presence, for your contribution, and for the fruitful discussion.
Thank you. Elizaveta, maybe you like to say a few words?
Thank you for thank you all for your presentation and this. I hope we'll meet next hour. Thank you.
Okay, thank you. Maybe somebody like to say some words? No? Yes? Okay. Welcome. Okay, dear colleagues, it was a grateful time with you. So we are very happy to be with you here, and see you next year. Bye-bye.
Thank you.
Bye. Have a nice day. Stay safe.
Bye.